Hey guys, this is going to go over the math examples that are in the notes, in the student notes and in the PowerPoint for the original momentum and impulse notes. You definitely need to watch the intro to momentum video first because that covers the concepts and the math will not make a lot of sense without those. Okay, so equation-wise, you found out in that intro video that momentum is symbolized by a P. It is measured in kilogram meters per second. And we calculate it by multiplying the mass in kilograms by the velocity in meters per second. It is considered the inertia of a moving object. So this V is important. It cannot be zero. It has to be a number. If we think about how we would change the momentum of an object, we have to change the inertia, right? So in order to change the inertia of anything, you have to apply an unbalanced force. So applying an unbalanced force for some amount of time is what we call an impulse. This is the thing that you do. For example, pressing on the brake pedal in your car or pressing on the accelerator in your car. Okay, and our equation is this one down here that says J, or impulse, equals a force, an unbalanced force, times some amount of time it was applied. Okay, and then when you do that, you're going to have a result, which is the change in momentum, right? So you press on the brakes, and the result is your car slows down. The equation is going to be this one here. Delta, remember, is change in, so delta P is change in momentum. And typically for us, it's going to equal a change in a mass times a change in velocity. Okay, and then what was really important also in that intro video is that you saw that J, or impulse, was equal to the change in momentum for an object. So that thing that you did is equal numerically to the change in momentum in the object. So we're going to apply those equations to these math examples. Just as an aside, if you've lost your equation sheet from the first 9 weeks and you need another, you should be able to find one on your teacher's Canvas site somewhere. If you're in Upmore's class, I'm going to put a copy in this week's module, April 13th through 17th. So if you need another copy, you can get one there. Okay, so first we've got a bowling ball cruising down the hallway. We're going to start with just writing our givens like normal. So we see we have a mass of 8 kilograms. We're given a velocity of 2 meters per second. And our question is, what is the momentum of this ball? So we refer to our formula sheet, and we see that momentum is equal to mass times velocity. So in this case, we're just going to plug in numbers, 8 kilograms times 2 meters per second. We're going to multiply across, and we get a total of 16 kilogram meters per second. Now, momentum is technically a vector, so we should have a direction here. We didn't give you any kind of indication as to direction in this problem, but just know, moving forward, if you continue in physics, momentum is a vector, and you should have a direction with it. Okay. Second question, the bowling ball is going to roll into a pillow and come to a stop. So the momentum is going to change. Okay, it changes in over a course of 0.5 seconds. And we want to know how much force the pillow puts on the ball in order to bring it to the stop. Okay, so we know from the first part that the ball has an initial momentum of 16 kilogram meters per second. We know that the ball is going to come to a stop. So if you put those together, that gives you a change in momentum of negative 16 kilogram meters per second. Remember, delta usually means final minus initial. So that's where we got that from. Okay, we also have a given of a time elapsed, which was 0.5 seconds. And then the force is the question. So if you'll recall from the last page, we said that impulse equals change in momentum. We can write impulse out as force times change in time. And then we can plug in our numbers. So we don't know force, but we do know the time was 0.5 seconds. We know change in momentum was negative 16 kilogram meters per second. We're going to divide by the 0.5 on both sides to get F by itself. And so force ends up being a negative 32 newtons. That is the force that the pillow puts on the ball to bring it to a stop. And then our third question here is, what is the force that the ball puts back on the pillow? So you know the answer to this. Think about Newton's third law. It says for every action force, there's an equal and opposite reaction force. So if the pillow put negative 32 newtons on the ball, then the ball put positive 32 newtons back on the pillow. And that is it for the math in this unit, or in this part of the unit. I have a couple of conceptual practice problems for you. If you feel like you're kind of confused on the ideas of impulse, keep going on the video. If you feel like you're okay with it, then you might be able to stop and go ahead and work on homework. Okay, so first of all, as a reminder, impulse equals change in momentum. That's huge, huge, huge. So you have in this first one a soccer ball accelerating from rest to 10 meters per second, and you have a medicine ball going from rest to 10 meters per second. So the change in velocity is the same for both, right? However, the soccer ball has a small mass and the medicine ball has a huge mass. So if we're thinking change in momentum is mass times change in velocity, well, change in velocity was the same, so we can kind of ignore that, but mass was definitely not. Mass was much bigger for the medicine ball, so we're going to say that you would require more impulse to change the velocity of the medicine ball. Second question is slowing a car from 60 to 40 miles per hour or the same car from 40 to 10 miles per hour. Which one requires more impulse? Okay, so you have a change in velocity here of 20 miles per hour. You have a change in velocity in this car of 30 miles per hour. Both cars had the same mass, but this one is definitely a larger change in velocity. And so we're going to say slowing the same car from 40 to 10 requires more impulse. Even though the 60 miles per hour car was going faster, it didn't have as big a change, and you're looking for the overall change. Third question, which activity requires more impulse? Landing from a jump while flexing the legs, so that would be that guy, or landing from a jump while keeping the legs straight, that would be that guy. Okay, so think about this. You probably did this as a kid. You landed really straight-legged at some point, jumping off a stair or something. And when you do that, your muscles are not absorbing much of the force, right? And so you have a very short amount of time and a very large force. It hurts to land like that, right? You all know intuitively not to do that. When you flex the legs, so you bend when you jump and you land, you have a relatively long amount of time before you actually come to a stop, right? The whole time that you're bending your legs, you're still moving. And because of that, that means you have a small force. Ultimately, however, both guys started at some speed initial. They both came to a final velocity, so change in velocity was the same. They also both have the same mass, and so they had the same change in momentum. Therefore, they have the same impulse. So remember, impulse equals change in momentum. There might be different outcomes, like this guy over here might break his legs, and this guy might be fine, but ultimately there was the same change. Therefore, we would say there's the same total impulse. Okay, so in light of this, why would you want to flex? More time equals less force equals less pain, right? Short time, big force, you're definitely going to feel that. Okay, Felix and Digby are going to bungee jump. Felix says they should use a stretchy rubber bungee cord. Digby says they should use a strong metal cable. Who is right and why? So again, think about the time. Bungee cord, you're going to bounce, right? So big time, small force. Digby says strong metal cable. Well, metal doesn't have a whole lot of give to it. You're going to pretty much snap to a stop. So that's a real fast time of impact. Really small time of impact, which means a really large force. So Felix is definitely correct on this one. Do not bungee jump with a metal cable. Next question. What is the physics reason for padding dashboards? Same kind of idea we've been looking at. Dashboards originally used to be metal with no padding on them. So we don't think of dashboards as soft, but they're a lot softer than they used to be. They have quite a bit of give. And so again, when you've got give, that means you lengthen the time. And because you've lengthened the time, you've decreased the force. So small force, again, equals less pain. Okay, so examples of pole vaulters and film stunt artists employing this kind of physics. That would be when they land on a pad, right? If you're going to jump out of a window because you're a stunt artist, you don't want to land on the ground. That would be a quick time, that'd be a large force, and that would be a lot of broken bones. When you land on a pad, you have a relatively long time to come to a stop. Therefore, you have a small force and theoretically no injuries. Same idea here for people who brace themselves in an accident, more likely to have injuries. When you're tense and you've braced yourself, the problem is that you have less give. So less give, you're less flexible. Ultimately means that you're going to come to a stop in a faster amount of time. And when you have a small time, you have a big force. Okay, last week you dropped an egg onto a pad of some sort. Hopefully yours survived. But if it didn't, let's go ahead and think through the physics of it. Okay, so which one experiences a greater force? That would definitely be the one that breaks, right? The one that breaks hits the ground or hits the pad with more force. The eggshell couldn't withstand that and it breaks. In contrast, which one experiences a greater time to come to a stop? That would be the one that survives, right? Small time. Big time equals small force. And then last but not least, which one experiences a greater impulse? This is kind of a trick question. They were the same, right? So again, they both eggs, whether they survived or didn't, had the same change in momentum. Therefore, they had the same change or same impulse. And again, you can look at it like this. The one that broke, let me change my color, sorry. The one that broke had, try this one more time. Okay, so the one that broke landed really quickly and had a large force. And so because of that, it did not survive. The one that survived came to a stop slowly. So it had a big time and therefore a small force. But if you're looking at this equation here, the numbers have just reversed, they've switched, and so that is why you can say they have the same impulse. All right, hope that helps. Let us know if you're confused, call us and we can help you out.